Question 10 is just a vertical circular motion question. So we have this, basically it's just a circle here. You can read through this if you want. The circle has a radius of 1.5 meters. We have a mass m, and it starts up here, and it's moved slightly. So the initial velocity is still basically 0. It's just slightly moved, so it slides down the cylinder, and it makes an angle theta with the vertical. And the student's going to model this as vertical circular motion, outline the assumptions made. So I think the best way to approach this is just think about when you're doing a circular motion question, what kind of factor are you using? The first one you're using is the centripetal force, is going to be mv squared over r, and the only forces we take into account, if we just draw a free body diagram that we will be using later anyway, so we have the weight going down, of course, we always take that into account. I won't resolve it just yet, but we do resolve it, and then we also have the reaction force. But that's about it. That's all we take into account in our free body diagram. We're not told anything about friction or a coefficient of drag or anything, so we don't take any of those forces into account. The second thing we usually do is we do the conservation of energy as well, in which we have kinetic energy, which is mv squared over 2, and we also have potential energy, which is mgh. They're the only two types of energy we take into account. So one thing that you could say is that in our conservation of energy, we're assuming that there's only kinetic energy and gravitational potential energy. So we're assuming that there is only kinetic energy and gravitational, that's going to take a while to take out, gravitational potential energy. It's important to say that because potential energy could be like, you know, energy in a string or something from an elastic string. Potential energy, and that energy is conserved. In reality it isn't. Is conserved. So you could say, like, for example, no energy loss. Energy loss due to sound or heat, I suppose. You can kind of say anything here as long as it's valid, but these are just the things that come to my head. So you could also say that there is no drag, or there's no drag. There is no drag or air resistance, and there's also no friction on our free body diagram. And as well as that, we're not taking into account how big the mass is either. It says here a small object of mass m. So we're basically assuming that the mass, like, it doesn't have any size. If it did, we'd have to take that into account. We'd have to say, well, if it's a meter, if it's like 2 meters, okay, it won't be 2 meters long. If it's like 10 centimeters big, we'd have to take into account how long it is when it hits the ground, for example, that this part of the box would hit the ground before this part does. But we don't take any of that into account. So we also assume that the mass is very small, or negligibly small, I guess you could say, that you can ignore its size. Negligibly small. Again, you can kind of say anything. The marking scheme doesn't say how many points you need, but that's probably enough. In part 2, we're asked to calculate the value of theta when the object leaves the surface of the cylinder. So the fact that we use whenever something leaves the surface, or if like a string goes slack or something, well, actually not really if a string goes slack, slightly different, but basically we're assuming that the reaction force is 0. Because the reaction force, remember, is when the object pushes down on the circle pushes up with a reaction force. But if the circle isn't pushing up, that means the object isn't pushing down, so it's not touching the circle anymore. So we're going to use the fact that the reaction force is 0, and then as we said earlier, we're going to use two facts, as we always do in vertical circular motion, that the centripetal force equals mv squared over r, the radius, and we're going to use this version because v squared is useful in the conservation of energy, because in the conservation of energy we have mu squared over 2 initial kinetic energy plus mgh0, the initial gravitational energy, equals mv squared over 2 the final kinetic energy plus mgh1 the final potential energy. So by using the centripetal force that has normal velocity and not angular velocity, we can kind of substitute in that here in the conservation of energy formula. So we can start by doing a free body diagram just to look at the forces. I know I did one above, but it was a bit small, so... Right, so we have the weight going down, and we want to resolve that into components that are kind of going perpendicular and parallel to the reaction force. And we'll also have the reaction force, or... because then we can get the centripetal force, which is obviously acting towards the center of the circle. Now to find out where theta is, we have to do a bit of geometry. So you can see if we have a straight line down and then a radius, we have theta between those. So I'm just going to do a little sketch here. If I have a straight line down here, and then this right here is basically like a radius, because this is kind of going towards the center of the circle. That means that this angle here is theta. Now, since this line is parallel with this line, they're both vertical. That means that these are alternating angles, and this is also theta. So that's how we can figure out theta, or where theta is in our free body diagram. I'm just going to get rid of that for neatness, but you should probably leave it in to show where you got it from, which means this is going to be mg cos theta. This will be mg sine theta. Oops. So the centripetal force is basically going to be going this way towards the center of the circle. So that's going to be equal to mg cos theta is helping it. So it's going in the same direction. It's positive, minus or, because or is going the other way. But or is 0. So that means, I'm just going to move this down a bit, that mv squared over the radius, which is 1.5, it says in the question, equals mg cos theta. We can divide both sides by m. We get that v squared, I'm just going to bring the 1.5 up, equals 1.5 g cos theta. So we know what v squared is, and we can probably sub that into our conservation of energy once we do that. So let's look at our conservation of energy. So basically we have mu squared over 2. The initial velocity is, we assume it to be 0, which is another thing you could write in your assumptions here, because we say that it's slightly disturbed from rest. So basically it's barely moving, but it starts slipping down. So that's going to be equal to 0. So we have 0 plus mg, and then the initial height is just the very top up here. So this is one radius, and then we have another radius. That's basically a diameter from the bottom to the top. I'm just going to take the bottom as my reference point. It usually works the best. So up here at the top, we're 3 meters above the ground. So we'll have mg times 3 equals mv squared over 2. We don't know what the velocity is. It could be anything. Plus mg, and then the height at any point. We have to do a bit more geometry for this. So if we want to find the height here, for example, after an angle theta, what we can say is we can see this right angle triangle here. And then we can have this part, which I'm just going to call b, because a is for acceleration. Don't want to mess that up. So b is this distance here. Okay? So this is like the vertical height, and we can just figure that out. So we have a little right angle triangle. I'm just going to get rid of this for now, but again, you don't want to be erasing things in the exam just for space. You could redraw this diagram below probably, but just for the video, we have theta here, we have 1.5 here, and we want to find this b, this height. So b is going to be 1.5 cos theta when you do the trigonometry, which means this is the vertical height, but then we're also 1.5 meters above the ground. So we have this 1.5, and then we have this b, which is depending on whatever theta is. So the total height, h1, is going to be 1.5 plus 1.5 cos theta. And we can just use that down here. So mg times 1.5 plus 1.5 cos theta. We can divide across by m, and we get 3g equals v squared over 2. I might multiply across by 2 as well, actually, to make things easier. So we can say that 6g equals v squared plus, and we'll multiply this by 2. We can factor out a 1.5. We can say 3g times 1 plus cos theta. Sorry if I went through that a bit fast. You can kind of do the simplifications yourself. And now, since we're looking for theta, the value of theta, we can replace this v squared with 1.5g cos theta, because that's from up here. So we'll have 6g equals 1.5g cos theta, and then of course we're going to have to expand this out to get the rest of it, because then we'll have 3g plus 3g cos theta. We can actually divide across by g, bring this 3g to the other side, we'll get 3 equals, and then 4.5 cos theta, which means that cos theta is equal to 3 over 4.5. I'm sure you can simplify that. So that's equal to 2/3, and so cos theta is 2/3. So theta is the cos inverse of 2/3, which is equal to, it's about 48.19 degrees, and that's the answer for theta when or is 0. Calculate the velocity of the object when it leaves the cylinder for part 3. This is very easy. V squared is 1.5g cos theta. Copy that down here. We know that cos theta is 2/3 from here. So that's equal to 1.5g times 2/3, which means that v is equal to the square root of 1.5g times 2 over 3. You could get a decimal on that, or you can notice something that works out nicely for future calculations as well, is that 1.5 times 2/3, they actually cancel if you put that into your calculator. So v is actually just the square root of g. And if you want to get a numerical thing on it, just in case, because you probably should, first of all, it's g meters per second. You should put in a unit usually, which is the same as, if you want to just put a decimal in for just in case, 3.13 meters per second. And that is the answer for V once it leaves the cylinder. In part 4, basically the student's going to model the motion of the object as projectile motion in a uniform gravitational field. This just means uniform gravitational. It means there's uniform acceleration, so there's no drag, no friction. Well, there won't be any friction, it's in the air, and gravity just is obviously acting on it. Calculate the time between when the object leaves and when it hits the ground. So basically, we're going to be looking at the j velocity here, the kind of vertical velocity. And first of all, to do that, we're going to have to see what the velocity is in terms of I and j. So we have our diagram up here. I'm just going to erase what I did here since it's not relevant. But again, you should be doing this on a separate diagram. So when you think about it, once it leaves, let's say it leaves the circle here, the velocity will be going obviously tangent to the circle, because that's just how the velocity works, because obviously it's not moving inside the circle, it's moving kind of on the circle. So as it leaves the circle, the velocity is going to be at a 90-degree angle to the radius. So just, I'm not going to draw that in because it gets a bit messy, but keep that in mind. We want to resolve it into I and j, so like that. We can do a similar thing here. Notice that this two are parallel, which means that this angle here is theta. And then if this whole angle is 90, that means that this angle here is 90 minus theta, which means you could use that angle, but that means that this angle is theta since that one's 90 and they cancel out. So we basically have V going down. So what we have, again, do that on another diagram maybe. So what we have is V going down, we have a right angle triangle, and this is theta. So this will be V sine theta, and this will be V cos theta. Now you can just use your value for V here and use your value for theta here and calculate those, but I kind of like to do things very accurately. You don't have to, but I like to. So first of all, for V, I'm going to put it in as root g. So the total velocity will be equal to root g, and we're going to look at j first. So cos theta is 2/3 as we have up there. So we'll have 2 root g over 3, 2 root g over 3i, and then the j is going down, so we'll have minus. And now instead of doing sine of this angle, if cos of theta is 2/3, so we can write down that cos of theta is equal to 2/3. That implies that we have a right angle triangle, and if we have theta here, cos is adjacent over hypotenuse, so we have 2, 3 here. We need to find this side, which we can just call, I don't know, x, why not? 2 squared plus x squared equals 3 squared. So we get that x is equal to the square root of 5 when you do that out. So we'll have root 5 here. Whoops. So we'll have root 5. Therefore, sine of theta equals opposite over hypotenuse, which is root 5 over 3. So we'll have minus root 5 over 3 times v, which is root g. And that's j's. Root 5 times root g is just root 5g, because you can combine them under the roots. And so that's that's our main factor we're using here. And how far are we above the ground? Well, basically, our height at any point is given by 1.5 plus 1.5 cos theta. So the height is given by 1.5 plus 1.5 cos theta. And we know that theta, in this case, it just left the circle. That means that cos theta is 2/3, as we calculated up here. So 1.5 times 2/3. Put that into your calculator. The 1.5 and 2/3 here cancel, giving you 1, and you get 2.5 meters. So that's the height. So we know this is the distance it is above the ground. We know its velocity. Now we can use Suvat equations. SUVAT. You could have done this at the start to see what you needed, but I was just kind of thinking on the spot. So acceleration is always minus g. We have to go down 2.5 meters. Our initial velocity in the j direction, since we're talking about hitting the ground, is minus root 5g. Oops. Minus root 5g over 3. And we're looking for the time taken, I believe. Yet the time between when it leaves the surface and whatever. So that's a question mark. We have SUAT. S equals ut plus a half at squared is the one we can use. So minus 2.5 equals minus root 5g t over 3 minus gt squared divided by 2. We can multiply across by 6 just to simplify a bit, and we'll get that We can also multiply across by a minus or cancel them all out, whatever way we want to think about it. So 2.5 times 6 is 15, which is equal to, we'll have 2t times root 5g, and then we'll have plus, and then times that by 6, you get 3gt squared. Bring it all to one side, we can just use the quadratic formula then. So that 3gt squared plus, we'll write it like this, 2 root 5gt minus 15 equals 0. So I just brought the 15 to the right side and then just kind of turned it the other way around. And now you can see we have a quadratic for t. So the quadratic formula, you should still write this out just in case. Negative b plus or minus the square root of b squared minus 4ac all over 2a, which is equal to minus 2 root 5g plus or minus the square root of 2 root 5g squared minus 4 times 3g times minus 15. Make sure that's all under the square root. All over 2 times 3g. Put that into your calculator, or at least some of it. So I'm just going to use a rough kind of approximation. We get minus 2 root 5g, and then we're plus or minus. Well, we can't have negative time, and since this is already negative, if we do another negative, the time will also be negative. So we're just going to be doing plus, just the plus. The square root of this big thing when you put it into your calculator is 44.27 to 2 decimal places, all over 6g. You can put that into your calculator then, and we get that t is equal to about 0.51 seconds. This actually isn't what is in the marking scheme, but I looked through it, and I think there might be a mistake in the marking scheme, because I think they had sine theta as root 5 over 2, but sine is opposite over hypotenuse. There's no way that's possible, so unless I did something wrong, which you could point out in the comments, that is the answer. And finally, part 5 asks us to calculate the horizontal distance between the point P and the point where the object lands on the ground. So the point P, I believe, is just when it leaves the circle. Oh no, wait, so point P is just there. So let's do an extra bit of geometry here. So remember when we were finding the height at any point theta, we did this right angle triangle. We said this was the height. This part here is going to be the horizontal distance it travels. So this horizontal distance is basically going to be 1.5 times sine theta, that's going across. Then it leaves the circle, and then we can use the Suvat equations with our stuff down there to figure out how far it travels after that. So 1.5 sine theta is from P to when it leaves the circle. So in total, we're going to have 1.5 sine theta, which is, and we got sine theta is just, root 5 over 3. So we'll have 1.5 times root 5 over 3, which we can just simplify to say that's root 5 over 2. That's only when it leaves the circle though. So we also have, after it leaves the circle, it takes 0.51 seconds to hit the ground. And we know that its velocity in the I direction is 2 root g. So we can set up some Suvat here, SUVAT. Acceleration is 0 because we're not neglecting drag or anything. Initial velocity, as we have here, 2 root g over 3. 2 root g over 3. Displacement is what we're looking for. And then the time taken is 0.51 seconds for it to hit the ground. SUAT, we'll have S equals UT plus a half AT squared, but A is 0, so that doesn't matter. So S equals 2 root G over 3 times T, which is 0.51. So that's our displacement. And if we add that to the root 5 over 2, so the total will be equal to root 5 over 2 plus 2 root G over 3 times 0.51. Put that into your calculator. You get that it traveled about 2.18 meters, and that's the answer. Again, that's not the answer they got in the marking scheme, but that's because they got a different value for time, because I think they calculated this wrong. But again, if there's a problem with that anyone notices, please let me know.